Lesson 29. Attributes of polygons. The objectives of the lesson are to classify polygons based on their sides and angles, and to find and use the measures of interior and exterior angles of polygons. The vocabulary for the lesson are side of a polygon, vertex of a polygon, diagonal, regular polygon, concave, and convex. Let's start with a definition. Each segment that forms a polygon is the side of a polygon. They're marked in red. The common endpoint of two sides is a vertex, and that is the dots in blue and all of the little labeled vertices. A segment that connects any two non-consecutive vertices is a diagonal. That would be in green. Other diagonals of this polygon would be AC, CE, BE, and CE. We name polygons by the number of sides that they have. 3 sides would be a triangle, 4 is a quadrilateral, 5 is a pentagon, 6 is a hexagon, 7 is a heptagon, 8 octagon, 9 is a nonagon, 10 a decagon, and 12 dodecagon. Anything besides that we call n-sides or an n-gon. If it's 15, it would be a 15-gon. Remember that a polygon is a closed plane figure formed by 3 or more segments that intersect only at their endpoints. Let's look at some examples of identifying or classifying polygons. So we want to look at each figure and decide if it is a polygon, and if so, we're going to name it by the number of sides. Well, what we have here is a figure that is definitely closed. If you count, you'll see there are 6 sides, so this is a polygon. It's a hexagon. Another example, we have this arrow shape. All of the sides are closed, and none of the lines go past their vertices, so this actually is a polygon. If you count the sides, you'll see there are 7, so this would be a heptagon. We have what looks like a crescent moon. This is not a polygon because we have curved edges. Anytime you have curved sides, they're not straight lines, they don't fit the definition of a polygon, so this would not be simply because of the curved sides. All the sides are congruent in an equilateral polygon, just like an equilateral triangle has equal sides. And the angles in an equiangular polygon, just like an equiangular triangle. A regular polygon is a whole lot like an equilateral or equiangular triangle. All regular polygons, no matter how many sides they have, all the sides are equal and all of the angles are equal. If they are not, if a polygon is not regular, it's irregular. When we classify them, we have one other means of classification, and this would be whether a polygon is concave or convex. Concave means that some part of one of the diagonals contains points on the exterior of the polygon. If no diagonal contains points on the exterior, then it is convex. All regular polygons are convex. Concave, you see on the left here, because we have an indentation, just like the arrow, we have one of the diagonals that goes outside. If it's outside of the figure, it's concave. These, you see the diagonals go clearly inside your shape, therefore it is convex. So we're going to decide whether it is regular or irregular and concave or convex. We see all of the sides are marked as equal. But what about the angles? This is irregular because although these two angles are congruent and these two angles are congruent, we would have to have all four congruent to be regular. However, it is convex because our diagonals would stay within the rhombus. Let's look at this. All of our angles are completely and totally congruent. They're all 90 degrees. But the sides are not all the same. So this would be an irregular polygon. And if I draw a diagonal from this vertice to this vertice, these two, they would be on the outside. So this would be concave and irregular. Then we have a square. It's turned on its side, but it's still a square. All the sides are equal. All of the corners, all of the angles are equal. The diagonals are clearly on the inside only. So this would be regular and convex. To find the sum of the interior angles measures of a convex polygon, we would draw all the possible diagonals from one vertex, only from one vertex of the polygon. This creates a set of triangles. Since we know that the sum of the angles of a triangle are 180, if we can count how many triangles we're able to make with one vertex of the polygon, then we have all the measures. We can add up how many triangles we have, therefore how many angles measures we have inside the entire polygon. If you notice in these diagrams, a triangle has 180 degrees. The quadrilateral, if I take a diagonal only from this vertex right here, I can make two triangles. So this would be 2 times 180, or 360 degrees. A pentagon, if I choose this vertex, I can draw two diagonals. So I have 3 triangles, so it would be 3 times 180 degrees. For a hexagon, I can draw 3 lines, which makes 4 triangles. So 4 times 180 degrees for the sum of the interior angles. Remember that we have 180 in each triangle. If we look at the pattern, we have a triangle with 3 sides. Number of triangles, well, that's 1, 180 degrees. The quadrilateral has 4 sides. We can make 2 triangles out of there. 2 times 180 is 360. The pentagon has 5 sides, 3 triangles, 540. A hexagon, 6 sides, 4 triangles, 4 times 180, which is 720. An n-gon has n sides. We subtract 2. If you notice, there's always 2 triangles less than number of sides. So n minus 2 times 180. So for however many sides your polygon has, you simply multiply 180 times n minus 2. In each convex polygon, the number of triangles formed is 2 less than the number of sides n. This gives us the polygon angle sum theorem. The sum of the interior angle measures of a convex polygon with n sides is n minus 2 times 180 degrees. So let's try to find some of these. Find the sum of the interior angle measures of a convex heptagon. Well, they didn't give us a picture, but we know it's a heptagon, which is 7 sides. If we subtract 2, we get 5 triangles. We use the polygon sum theorem. N minus 2 times 180. A heptagon has 7 sides, so substitute 7 in place of n. Simplify, and we have 5 times 180, or 900 degrees. Find the measure of each interior angle of a regular 16gon. Now in this case, we're not looking for the total sum, we're looking for the measure of each one. So first we need to know the total. Find the sum of the interior angle measures. We use the polygon sum theorem. N minus 2 times 180. Substitute 16 for n and simplify. So 16 minus 2 times 180 equals 2,520 degrees. Find the measures of one interior angle. The interior angles are congruent, so we're going to just divide by 16 as we have 16 sides, 16 angles, and we get 157.5 degrees. Find the measure of each interior angle of a pentagon ABCDE. So, if we look at our picture, they're all marked with C's. We have 18C degrees, 32C degrees, 32C degrees, 18C degrees, and 35C degrees. So, 5 minus 2 times 180 is 540 degrees. This is from the polygon angle sum theorem. So the measure of angle A plus the measure of angle B, measure of angle C, measure of angle D, and measure of angle E is 540 degrees. That's from the polygon angle sum theorem. And then we're going to substitute in what we know. So we have 35C plus 18C plus 32C plus 32C plus 18C equals 540. We combine like terms and we get that 135C is equal to 540. If we divide both sides by 135, we get that C equals 4. But we're not finished yet. We want to find the actual measures of these angles. So, we start with C equals 4. Measure of angle A equals 35 times 4 degrees, so 140 degrees. The measure of angle B and E are the same. That's 18 times 4 degrees, which would be 72 degrees. And C and D are equal, which would be 128. We want to notice patterns. In polygons, an exterior angle has been measured at each vertex. Notice that in each case, the sum of all the exterior angles measures 360 degrees. An exterior angle is formed by one side of a polygon and the extension of a consecutive side. This gives us the polygon exterior angle sum theorem. The sum of the exterior angle measures one angle at each vertex of a convex polygon is 360 degrees. Note this only works for convex polygons. So if we want to find the measure of the exterior angles of a regular 20gon, a 20gon has set 20 sides and 20 vertices. So using the polygon angle sum theorem, we know the sum of the exterior angles is 360 degrees. A regular 20gon has 20 congruent exterior angles, so divide the sum by 20. The measure of one exterior angle is going to be 18 degrees. Let's look at another example. We want to find the value of B in polygon FGHJKL. And if you note, B is found in each one of the angles. So using the exterior sum theorem, 15B plus 18B plus 33B plus 16B plus 10B plus 28B has to equal 360 degrees. We're going to combine like terms, and we get that 120B equals 360. If we divide both sides by 120, we get that B equals 3. Let's look at an application of using this. Anne is making paper stars for party decorations. What is the measure of angle 1? Angle 1 is an exterior angle of a regular pentagon. If you look in the middle of her star, this is a regular pentagon. Angle 1 here is just the extension of one of the angles. By the polygon exterior angle sum theorem, the sum of the exterior angles measure is 360 degrees. The regular pentagon has 5 congruent exterior angles, so divide the sum by 5. 360 divided by 5 is 72 degrees. Now you try. Tell whether each figure is a polygon, and if so, name it by the number of sides, and then decide whether 4, 5, and 6 are regular or irregular and concave or convex. Then you want to practice finding the interior measures of each convex polygon, the measure of each interior angle, and then the measure of each exterior angle.